Hello and welcome to this episode of T-Tech. On today's episode, we're going to cover the things I would learn if I had to start over again. So I do hope you enjoy this one, and let's get into it. Hello and welcome to this episode of T-Tech. We're going to talk about all the things I would learn if I had to start over. So we're going to start with the easiest thing to understand first. All the physical things, all the things that you can see and touch. Alright? So that is computer hardware. Now, computer hardware is made up of a lot of different components that all have a specific function. You have the motherboard, CPU, RAM, hard drive, a NIC, and a GPU. So we're going to start here with the motherboard. Well, the motherboard connects all the other components together. So it gives them a way to communicate, alright? Kind of like streets connect different parts of a city together. It gives them a way to, travel around. Now, the BIOS and the UEFI turns on and tests all the components in the computer. Everything connected to the motherboard. Okay, and that's called the post or power on self-test. In addition, on the motherboard, you have RAM slots and a CPU socket. You also have expansion slots that are called PCI, Peripheral Component Interconnect, and PCI Express, which is a newer version of PCI. So, the CPU goes into that CPU socket. Okay? It stands for Central Processing Unit. It's mostly known as the brain of the computer, okay? Its job is to run instructions one by one, okay? Now, the CPU uses the RAM to store these instructions. And the reason is, if there's lots of instructions, the CPU can't hold them all at once to work on them. Okay, so it has to store them in RAM and get them periodically. Now, with the CPU, though, the speed, or the frequency, is how many instructions you can run on it per second. Alright, so that determines that. So the speed is like your gigahertz or megahertz. That's the speed. And, the frequency, but that is also the same as saying speed. So the cores of a CPU, that allows you to run multiple sets of instructions at a time. So it's kind of like if you had two desks in front of you, okay? You could, in theory, do twice the work at once and have the work done in less time. It's the same idea with cores on a CPU. So, the RAM, as we just had touched on, the CPU and RAM communicate together, and the motherboard connects it all together. So it stands for Random Access Memory. It stores the instructions. So anything you can think of. When you open a program, it's stored in RAM to be operated on and run, okay? And it stores instructions. Similarly to the CPU, the frequency is how fast it can read and write those instructions, okay? Faster the frequency, you're able to send and receive data from RAM quicker. Same thing with the CPU. So again, the CPU reads and writes instructions from RAM, and they have that relationship together to send them back and forth. So the hard drive, its job is to permanently store the instructions. Alright, so when the computer's off, it will remember all the instructions, okay? So it reads and writes instructions to the CPU upon request. So the CPU is orchestrating these things. We'll see that in a little bit, but it stores instructions. That's what you got to remember. So the NIC, or Network Interface Card, it sends and receives data to and from other computers, okay? And the data is called packets, but we'll get to that later. But that's its job. And it, again, reads and writes data to the CPU upon request, and we'll see that in a little bit. So the GPU, this is the graphics processing unit. Its job, it draws images very fast. So in, like, let's say right now you have A PS4, your phone has a GPU in there. A gaming PC, you buy a GPU and put it in there. But the whole point is so it can draw the images very fast, so the CPU doesn't have to. But the CPU still has to get the data to it. So that's why it reads and writes data to the CPU. So hopefully this will make sense here. This is our motherboard. And there's our CPU connected in. Here's our RAM, because RAM will come in modules of different sizes. There's your hard drive that's storing the instructions. And here's your PCI and PCI Express slots. Your NIC can go in a PCI slot. They can also be integrated in the motherboard. And here's your GPU, which is in the PCI Express slot. Now, there's one more thing about the GPU. Just like how the NIC can be integrated, the GPU can as well. It is integrated in phones and laptops and things, which means it's a chip that's similar to your CPU. It's integrated in there, and it's able to do the same thing, but just take up less space. Alright, so down below that, this is what I'm saying about the CPU can send data from RAM to and from RAM. It can send from the hard drive, the GPU, and the NIC. When it loads a program, it has to get it off the hard disk or hard drive and send it to RAM. The extra pieces it's not working on right now works on those pieces, sends it back to RAM, maybe the completed operation it's doing. And if it needs to save the data back to the disk, it has to go back through the CPU to the disk to be stored. Alright? So this was the first part here, all about computer hardware. So I will see you in just a second. Alright, welcome back. So we just talked about the physical hardware, okay? And we talked about how it all communicates through the CPU and that instructions go in and out of all the hardware, okay? Where's the thing? The hardware by itself cannot do anything without instructions. So this is where we talk about the boot process and the OS, alright? The OS stands for operating system, by the way, but we'll get there in 1 second. So the BIOS, or the UEFI, like I said before, performs a post-test. That tests all the hardware on the motherboard. Now, if that does fail, it will either beep, or some motherboards will blink a light, okay, to give you an indication of what's wrong, because those are well-known error codes, and you would just go and look them up for the manufacturer. But what it does after the hardware is all working, like mine right next to me, it beeps. Okay, it beeps and then it goes to the next point. After this, though, it looks on the hard drive for a bootloader. Okay, and what the bootloader does is it looks on the hard disk for a kernel. Alright, so once the BIOS finds the bootloader on the hard drive, those instructions for the bootloader, first thing is when you click the power button, the BIOS loads into the CPU. Okay, that's the first thing the CPU knows. It knows how to get those instructions and start processing those instructions. The BIOS knows a little more. And what the BIOS knows is how to look for the bootloader. And the bootloader is the first thing on the hard drive. So when it finds that, the CPU then goes into loading the bootloader's instructions in. Alright, and after it does that, then the bootloader knows more than the BIOS, and it looks on the hard drive, but further onto it, for a kernel. Okay, now the kernel is the operating system. Okay? Now then again, as we said, now the CPU is going to start loading the kernel's instructions in and start to operate on that. So the kernel runs its instructions after the bootloader finds it, and then the kernel starts to load more information, programs it needs, also called a user land, okay? And that's when the CPU will be pulling more instructions off that hard drive and into RAM, all because the instructions in the kernel are telling it what it needs. Okay? So, again, the OS is the operating system, and an operating system consists of a kernel and user land programs. All right? The kernel, its job is to manage all the computer's hardware. All right? All the components we talked about in the first part. And the kernel controls what resources the programs can use. Resources, I just mean hardware by saying resources, okay? But it's very commonly called that. Now, the scheduler in the kernel, okay, that controls how long programs can use the resources. If you didn't have a scheduler, a program like Firefox could run forever and not let anything else happen, okay? That's why we need a mechanism to limit the time that a program can do something. So, drivers interact with and control the computer's hardware. They are things like drivers for your hard drive interface. They need a way to know how to talk to the hardware and tell it when it should do something. And vice versa, though, the drivers listen for hardware interrupts from devices, and then they send that data to another part of the computer. So if a program needs to get data to the hard drive, the program does a system call. So it basically just says, hey, I need to do this. And anyway, it goes, the operating system uses its driver, tells the hardware it needs to do something, and then the hardware does it, and then we'll send a result. The opposite end of that is if the hardware has something that it needs to tell the operating system, any data, etc. So then what happens is it sends a hardware interrupt, and then the driver processes that and gets it to the rest of the kernel, then the kernel gets it to that program. So this is how the process looks. The BIOS of the UEFI, it does that power on self-test. If it passes and it's got a check mark, the BIOS looks for the bootloader. All right. Once it finds the bootloader code looks for a kernel. The kernel then starts booting. And once the kernel's done booting, you get your user land. And then these are things like in Windows, this could be your login program. That's an example of user land. So, the idea after that is processes request resources. And these are simply called system calls. And what happens is, like, let's say Firefox wants to get to the internet. Well, there's lots of things Firefox needs for that, but an example would be it needs to use the hard drive for a little bit. It needs to obviously have CPU time, and it needs to use things like the network card. Well, it has to tell the kernel it needs those things. That's why it requests resources with system calls. And then the scheduler's job in the kernel says, he's got like a clipboard. He's like, all right, you can use the network interface card for, 5 seconds. You can use this much CPU time for 10 seconds. You can use this much RAM because it's all allocated. So, after that, though, then the drivers and hardware would help that process indirectly get the data it needs. Again, using the NIC, using the hard drive, using the RAM. All those kinds of things. So this is how it all happens, and it just kind of goes in a loop like that. Processes request resources, the kernel goes down, uses its scheduler to schedule those. The kernel uses drivers to get to the hardware to use those resources, and then the hardware gives information back to the drivers. The drivers send that back to other parts of the kernel sends it back to the process. Okay? That's how all this is how hardware is controlled. Okay? The hardware can't control itself. it needs instructions to tell it what to do. So in the next part, though, we're going to get into what those instructions really are. And, when I keep saying program, we'll pull the curtain back on what it is. So I'll see you in a second. All right, welcome back. So, how I said, instructions and programs. Well, what those are binary, and those are represented in bits and bytes. All right? This is what instructions are in a program. So binary is how the computers see information. They don't see, like, if you have, LibreOffice or something, they don't see, if you're typing a word like hello, they don't see each letter, like the H or the E or anything like that. They see, like, it's called ASCII. The letter is represented by a string of binary. And that's how the computer knows it should show you an A, because when you type A, what's sent is a string of binary that tells it, okay, I know what A is, and then sends it back. Even though it really doesn't, it just knows the string. But how it does that, it uses a 0 or a 1, and that means on or off. It's actually really cool because in electronics, your power, your electricity is on or off in digital circuits. So that's why zeros and ones very nicely line up with that. So a single 0 or 1 is a bit. That's the smallest information a computer can see and process. And what happens is, when you take those bits and combine them into groups of 8, that's a byte, B-Y-T-E, okay? And another fun one that isn't talked about hugely is when bits are combined into groups of 4, that is a nibble. Now, I just mean the word nibble because you don't usually see it all the time. And it threw me the first time I saw it too. But anyway, 8 bits is a byte, 4 bits is a nibble. So how are these bits and bytes used? Well, they're actually used in 2 very important ways. Now, first of all, in telecommunications, in computer networks, bits are used like 1,000 bits is 1 kilobit. It's bits used, not bytes, okay? So 1,000 kilobits is 1 megabit. 1,000 megabits is 1 gigabit. 1,000 gigabits is 1 terabit. And 1,000 terabits is 1 petabit, okay? On the other side of it, in programming, we use bytes to represent information, not bits. So 1,000 bytes is 1 kilobyte, 1,000 bytes. 1,000 kilobytes is 1 megabit, okay? 1,000 megabits is 1 gigabit, and so on. The thing is, though, the programming side of it is how we represent things like file sizes, or the amount of RAM we have, or the amount of hard drive space. But those are still bits at the end of the day. They're just grouped together in that way to make them a byte. And, and or megabyte, gigabyte, terabyte, okay? I hope that made sense, but you have 2 different ways to use these. So a very important thing in programming or in telecommunications is counting in binary. So in a byte, each bit of that byte has a decimal value. So just like the numbers we normally use as humans. So in a byte, they have the value, and binary, though, is calculated in powers of 2, also called base 2. So that is different than the base 10 system we usually use. But anyway, we have a binary bit here. The thing is, it doubles. So there's 8 bits here. Actually, move my mouse here. Okay, there we go, right here. It doubles. So 1, 2, 4, 8, 16, 32, 64, and 128. It's very simple to count in binary. if a 1 is on, because it can be a 0 or 1, if a 1 is on, you just remember where those decimal values are up there in your head and add the decimal numbers together. It's that simple. That's all it is. So if a 1 is on here and it goes from right to left, okay. If a 1 is on, I just bring that down in my equation and put a 1 in. That's all I need, because it's essentially 1 plus 0 plus 0 plus 0 plus 0 and so on. I don't have to add the ones that aren't on, aren't ones. So that will come out to 1. In this example, they're all on. What do? 1 plus 2 plus 4 plus 8 plus 16 plus 32 and so on. And then bring that down in the equation and it equals 255. And that is how computers count in decimal. Simple as that. And how we represent it in our own heads to understand what we're being shown by a computer and to understand how they work. But that's the main idea. And now the main important thing, if you're doing programming or telecom or anything like that, the computer will only starts at 0, just like, decimal, so it's 0 to 255. Why does it stop at 255? There's only 8 bits in a byte, and you can represent 255. Now, it doesn't stop there. You just keep adding bytes together. So in this case, to finish this out, if we added another byte there, that would be 255 and then another 255. So we could just keep counting. It just keeps doubling. That's the really fun thing. It just doubles, like from 128, it doubles to 256. From that, 512 to 1024 to 2048, 496, 8,192, and 16,384, and it just keeps going. But up to 16,384 will help you in programming and help you in telecommunications, so you really want to memorize those values of doubling. I've done it for a long time, so it just keep practicing it and it becomes second nature. But with that, that's what programs are and how to use bits and bytes and how to count on them and what they are. So I'll see you in 1 second. Okay, welcome back. So in this one, we're now going to talk about computer networking. So we talked about, the hardware operating systems, what instructions are. So now this is talking about computers need to send information, those instructions, the binary. How do they do it? Well, this is very simply how computers send information to each other. And I'll tell you right out, this is my favorite thing in the entire world. So computer networking is what I really like to do. But anyway, it uses rules, also called protocols, called TCP/IP. All right? And to understand that, there's 2 models to understand the pieces of a network and the problems we're trying to solve. So you have the OSI model, or the Open Systems Interconnection model, and the TCP/IP model, also called the DoD model. Now, the TCP/IP model is newer than the OSI model, but the OSI model is one we most commonly reference. There's 7 layers to the OSI model, and they're, as you see, application, presentation, session, transport, network, data link, and that also has a sublayer in there called LLC, or Logical Link Control. And the last layer is physical. You can memorize them from the bottom or the top, but the main important thing is that you memorize them. Now, the TCP/IP model is, what they did was they took session and presentation from the OSI model and combined it into one layer called application. And with TCP/IP, you have the application, transport, network, data link, and physical. Now, there is about 4 different representations, versions of the TCP/IP model. There's also one that has internet in place of the network layer. So just know it's different combinations of taking the OSI model and shortening it, basically. But when we're talking about this, and we're talking about network problems, or we're working on a network, you use the OSI layer numbers, not simply the TCP/IP, because some people will use one, and some people will use the other. So the layer 7 handles the protocols, and these are all the instructions. Things like FTP, HTTP, HTTPS, DNS, things like that. And those are what things like Firefox use to get you web pages and things like that. Layer 4 is the transport layer, and that handles protocols like TCP and UDP. And those are responsible for sending the information between the applications. And it also uses port numbers to do that, okay? Layer 3, and there also is source and destination port numbers. I should mention that. Layer 3 is the network layer, and this deals with IP, IPv6, and ICMP. And this is where you'll hear the term IP addresses. An IP address just identifies a computer, but basically it has a source address and a destination address. And layer 2 is Ethernet and things like that, and PPP and HDLC. It handles the things with the network card, okay? And layer 1 handles all the physical stuff, like UTP cable, otherwise known as Ethernet cable, radio waves with wireless, or your fiber, and all those things that go with that. Or your cabling for your cable modem and things like that. So anyway, the computers use a MAC address, and that identifies the frames. And the frames are what is sent by the network card. They also use an IP address to identify packets they send. There's both source and destination MAC addresses and IP addresses. And a network is just a group of computers that are in the same IP subnet. And a subnet mask lets computers figure out what group they're in, okay? So that's how they know what group they belong to. And speaking of the IP addresses, in a computer network, special computers that are called routers, they use IP addresses to route the packets, okay? They have a source address and a destination address, as we just spoke, and then the router looks at the destination address, and it holds different routes, so different streets, basically, in its routing table. But what it has to do is find the best route for that destination address in the packet. Now that route is paired with a NIC, and the packet is sent out of it. And a very important term, when that happens, it's called packet forwarding, also known as IP forwarding. So it's forwarding the packet one step further to where it needs to go. Now, a very important term. When you hear an IP subnet, or subnet, that's what's called a broadcast domain. The easiest way to explain it is it's basically like how far, if a computer yells, how far is it going to go? Okay, if a computer yells, how far away are you going to hear it? Very simple, that's what it is. So the routers, though, they're like the wall. It's going to stop the noise from those computers getting anywhere else. All right. So anyway, the routers break up broadcast domains. Okay, that's what it's called. So each IP subnet is a broadcast domain. So each network, in other words, and that's the group of where your computers are. And the routes, you can either learn them statically, so we can type them in to a router, or you can use a routing protocol, and that would learn them dynamically. So let's just break this down. We have our routing table. It has different networks. And this /24 here, that is something called CIDR, okay? And that means classless interdomain routing. But I'm going to leave links at the end of this so you can read more about all this stuff because it's very fascinating. But the PC sends a packet up to the router on link D, Okay? And the packet has a source address of 192.168.1.254. And by the way, where do you think it comes up with those decimal values? It's strings of binary. That's all it is. It's just bytes. But anyway, it has that destination address. And what the router does is sees that that destination address falls in this subnet. And that subnet is out of link B. So what it does is just sends it out of link B. And then when it comes back, it would just send out a link D because it would be then destined for who sent it. All right? Now, these are the different classes of addresses. And the value has to be that in the first octet, okay? And those are the different subnet masks and or CIDR that apply to all this. But again, this gets in depth, but it's very fun. Computers can talk in different ways, and that determines the data flow. And unicast is a one-to-one, so it's like me talking to you right now. It's one-to-one. Now, multicast means one to many. So if I'm giving a conference, I'm talking from myself to a bigger group of people, but only the people that came to that conference get to hear me. Okay, likewise, with multicast, the computers have to want to hear that information. Now, broadcast is just like I'm going out and just yelling as loud as I can. I don't care who hears me. Okay? Just want to get to everyone all at once. And Anycast is called one to closest. Basically, it's a way that the computer wants information, but it wants to get it only from the closest place to get that information. It's like, I gotta go to the store, I gotta get milk or something. I'm gonna go to the closest store to get that milk. Alright? Basically the idea of it. But the other ones here are just private. And again, I put them there to get your mind going about these things so you can search it on your own. Alright? But basically those are just groups that aren't used on the internet. But anyway. With the MAC addresses, we have special computers called switches, and they use MAC addresses to switch frames. Very simply, they have a source and destination address like before, and what the switch does is it just uses the destination address of the frame, and instead of a routing table, it uses a CAM table to find the correct port. All right? And they build that table by looking at source MAC addresses. And just like a routing table, that belongs to a certain port, and they send the frame out of it. And when they do that, it's called switching frames. So frames stay within the same IP network, and this is where broadcast domain comes back in. The switch doesn't normally connect multiple networks, okay? It just connects PCs in the same network. So everything connected to a switch is in one broadcast domain. If a computer yells, everyone's hearing it. Okay? Now, each computer that is connected to a switch port is its own collision domain. So basically, they don't have to share. You have basically a separate dinner plate. You don't have one plate you have to share off of. But that's how to think of a collision domain. All right? So switches can make more broadcast domains, but they do this at layer 2. And that's when you do that, that's called VLANs. All right. But anyway, we have our CAM table, our source MAC address of PC1 and the destination. The switch gets it, and he's looking for that destination. The two MAC address of all twos almost is link C, so it sends it out to PC2. Very important. It only sends to PC2. PC3 won't hear it, okay? It's not destined for its MAC address. But the other thing is when they want to know where PC2 is, they do yell first, essentially. And then that goes everywhere. But once the switch finds the source MAC address, it only sends to the one PC. Now, how MAC addresses are, how we see these decimal, it's not normal. It's not just straight decimal. It's something called hexadecimal. And we have our binary, but we just break it up into 4-bit chunks, those nibbles. And what happens is you have the values represented here in 4 chunks. All you do is you take them, and the values here are 1, 2, 4, 8, because we only have 4 bits. And you just add the decimal together. So all we do is add 1 plus 2 plus 4 plus 8, and that makes 15. In hexadecimal, though, you don't just write 15. It is represented by the letter F. So this is why all those are on. So it's all F's. And then these are F's. Okay? And this is actually, I've omitted some of the strings of binary, because each section is 1 F. Okay? Each group of 4 ones would be 1 F. Just wanted to add that so you're not confused. But the last main thing in a network is servers. So the servers just provide information to clients, and those are our PCs. And again, the rules and protocols are going to determine what conversation they have together. And the whole idea is they use the network to communicate to each other. So there's one more type of server. It's called a peer-to-peer server. That's when a client can be both a client and a server at the same time. Now, this is an example of those layer 7 protocols and the port numbers I talked about. The port numbers identify the protocol, and the protocols are served by the server. There's lots of different server programs for all these protocols too. And when we put all this together, when we combine all 3 of those things, we have the internet. It's also called the network of networks. So you have your client, he's connected to a switch and another router. The routers are doing their thing with the IP addresses, as we talked about, using those routing protocols and the routing tables. The switches are using the frames in the CAM table. Server is using its conversation rules for all its protocols. And the routers are dynamically learning all the routes by these routing protocols up here. And again, a lot of that, but that's a lot of fun to learn. I urge you to go out and look all the stuff look up all the stuff in this video and learn all you can about it if you're interested. So that is all for this part, and I will see you in 1 second. Alright, so the last thing that's very important is computer programming. So programming is simply how you tell a computer how to solve a problem. So you have a problem to solve, and it's easier to solve the problem using a computer, and that's why you program a computer. Okay? So it's done with programming languages, and those are just different ways to solve a problem. So that there's multiple programs that are written in different programming languages, and they can be all there to solve the same problem, just in a little bit different way. Now, this is where all the binary bits and bytes and operating systems and all that kind of come in, because all programs are just sets of instructions the CPU runs. All right? And those instructions are just, the CPU sees them as binary, and it will execute them. So when you execute a program, it's the CPU running the binary that represents that program. Now, there's 2 important distinctions with programming languages. They can either be, 1, interpreted or compiled. So the differences there are very important. Interpreted languages are ran in a way, well, when the computer executes the code, it has to run each instruction and then change it into binary dynamically as it runs each one. It's quicker most times to make a program just in an interpreted language most times, and it's more portable, but it's not as fast to run. Okay? So Compiled, though, you have to type the program completely, and then you have to make sure everything's typed correctly, just like interpreted. But you have to do an extra step. You have to run it through a compiler to turn it into the binary that the computer will run. And that also carries with it something called CPU architecture. And that program, when you compile it, it has to be compiled by a compiler for the CPU architecture. If you search some of these things, you'll hear terms like ARM, 32-bit, like Intel 32-bit or Intel 64-bit, PowerPC. Things like that are all different architectures, and they don't understand the same compiled programs. But with interpreted, as long as the interpreter is compiled for that architecture, you can run it across any CPU. All right? Simple as that. So because of that, they're more portable. But programming languages, though, speaking of solving problems, they have modules and or libraries in some languages. And the whole thing is, if I say solve a problem of, what's 2 plus 2? It's 4. But if I solve that, I can make a program, a smaller program just to do that, and make it a module. The cool thing is, when somebody down the road wants to solve that problem, they can use my module to solve it, instead of having to write the instructions to the computer to solve it. So that's why modules and libraries are very important, because in operating systems, they've already figured out how to solve things like, how do I route an IP packet? How do I, read a disk, or any number of things like that. So that's why you have different programs that have modules that are solving those problems. When you want to make something new, you don't have to reinvent the wheel and start over, but just use the modules. So a little bit about programming that kind of applies to every language for the most part. Programming uses variables to hold information. So like, if I was doing 2 plus 2 equals 4, what I would do here is I would have variable like first number, and that would be the name of it, and then I would say that equals 2. All right? Then I would say something like second number equals 2. All right? This would be two variables holding different information. And I could then take it and add the two variables together. So add 2 plus 2, and what I could end up doing in the language is putting the result of adding the numbers into another variable. And then I could do many things with that, but like show the user the end variable. But I could use 3 variables to do that. Make a very simple program like a calculator, just to give you an idea of what you can do. But as well as variables, programs have functions in them. You create the function, and you break the problem into smaller pieces. So if I want to add the number, I want to, let's say, store the number in a file, and then I want to show the user the number. Those are 3 problems. So I could write 3 functions. I could write one function that has the variables in it, like I just talked about, that add the numbers together and give me a result. And then in the 2 other functions, I could take that same result and I could put it in a file in one function, in my second function, and then in my third function, I could tell the user what's up, what happened with it, what the result is. So the other thing they have, though, is something called loops. And loops simply repeat instructions over and over. There's for loops, there's while loops, and different things like that. An example would be packet forwarding, honestly. Router gets a packet, it has to look at destination address, look at its routing table, send it out that port. Well, that's very good to have that function that does that, maybe in a loop, because it has to do it over and over. So that's an example of using a loop. But there's many different implementations and ways you can use this. But as I said above, though, already, The interpreted languages are more portable but slower. The compiled languages are very fast but not as portable, again because of the CPU architectures. And just down below here, we have examples of compiled languages. That's C, C++, C#, Rust, and Go is another language. But C is used to write things like operating systems. Linux, I believe, is written in C++, and that's a kernel. That is an operating system. BSD is an operating system that's written in C. But yeah, it's written in that because those have to run very fast on one CPU architecture. But let's say if I want to go through a file that has a lot of names in it or something, I would use something like an interpreted language because I could write it quicker. It doesn't really have to run super fast, but it can run fast enough, but it may have to go across different computers and run on them. So that makes it easier. And examples of those are Python, Perl, in Linux and BSD, and in Windows, mostly Linux and BSD, but now in Windows a little bit. There's Shell. You have different command interpreters like SH, Bash, or C Shell, and you can make programs with that language as well. And they have the loops and they have all the things we talked about in them. There's also Ruby as well. But with that, we're going to now finish on some resources. I encourage you to go to these websites here and learn a little more about all the topics I discussed. I do hope it was enjoyable, and I hope it helped. I hope it wasn't just confusing. And in summary here of the entire video, the reason I went over the things the way I did and the combination and flow of it, I started with computer hardware because that's the base of it. And then I wanted you to realize that the hardware doesn't do anything without instructions, so that's why we need the kernel and the programs, the userland and all that, to guide, to manage everything and make the computer keep running. Okay? And, then we went over how all of that is represented, and that's how operating systems are written and all that, all the programs. And, how they communicate, because then once we talked about the first three things, we basically have the idea of what a single computer is. Then when we put in the internet there and the computer networking, then we're finding out that we can combine all the computers together and they can send and receive information. And with the programming language, I wanted to wrap it up with that because the reason is this. The hardware, it is the physical part, but the operating system, the computer networking, the all of the other, and all the processes that hardware can do, routers, switches, and all that, it's all software. So that's why I ended with programming, because programming makes all that stuff work. And all that is, it's just all these problems we had to solve over the years. That's why we tell the computer to solve them with a program. The last thing I would add is quantum computing. What I showed with the binary was something called classical computing. Okay, with quantum computing, you can represent more information a lot. It's basically a more advanced form of computing, and that's going to be taking off in the next 5-10 years, I'm sure, in some form or another. They have things like that now. They can transmit the thing they use called qubits between computers. So we're kind of reinventing computer networking, but we're going to use quantum computing, so it's going to be very fast and everything. At least that's what it seems to be going toward, but and I could be totally wrong, but I just think that's where things are headed. So with all that, Tyler with G-Tech, hope you enjoyed the video and have a nice day.